Okay, so here we are. Someone asked about, on the final. You're allowed a full sheet, both-sided, of notes, handwritten notes for the final. They have to be handwritten, but you get a full sheet. Or you can use your 4 half sheets, right? One for each exam, half sheet, one-sided for each exam. Either one's fine. Okay, so security code is made up of 4 digits, 0 through 9, followed by 2 letters. So here I have 6 different decisions I'm making. Maybe I'll go ahead and just white this out. Right, making 6 decisions. So 6 different spots down here. How many options for my first choice? Digits, 10. How many options for my second choice? Digits, I have 10 digits. Next choice, 10 because you can reuse them. How about letters? How many options for the letter? 26. And the last letter, also 26. Good. And then, remember, you take the number of, it's like that tree, right? You take the number of decisions, or sorry, the number of choices for each decision, and you multiply them. So here I have 6 different decisions I'm making. I'm going to multiply, actually I'm going to use red instead of like red. I'm going to multiply each of these numbers. And how do you remember that? Go back to think back to shirts and shorts, right? Or shirts and pants. You have 2 pairs of pants and 3 shirts. Just don't use 2 and 2 because that is symmetric and all that stuff. So if I have 2 pairs of pants and I have 3 shirts, so if I took jeans, I could have 3 choices here. If I took khakis, I have 3 choices there. So all together, I should end up with 6 different possible outcomes. That's 2 times 3, not 2 plus 3. So it's kind of an easy way of kind of reminding yourself of how to, what you do with these. You multiply and you don't add. 2 plus 3. Oops. So whenever you're trying to figure something out, go back to the very basic, very simple example, and then that kind of makes it a lot clearer. All right, so you should end up with 6,760,000 as your answer. And then we'll take a look at this one here. First, were there any questions on that last one? I didn't see any. All right, go ahead and ask if you have any. All right, so I went ahead and filled in the totals here. And then they like broccoli, 51 like broccoli out of 100, so that's 51 over 100. They're probably either a man or a child. So there's 38 men, there's 22 children, there's no overlap. So you just add those, 38 plus 20, 22, and you end up with 60. 22. And then probably they're a child or likes broccoli. So there's 22 children, and there's 51 who like broccoli. But here's the thing, this 10, it's getting counted in the total broccoli people, and it's also getting counted in the total children. It's getting double counted. It's getting counted in the 51 and in the 22. So you have to subtract off one of them so that it only gets counted once. And doesn't get, it's the overlap. You have to subtract off the overlap. So then you should get 22 plus 51 minus 10 is 63 out of 100. And the last one, dislikes broccoli and is a man. So you might think, and I multiply. That's true. However, this is a table. Don't make it harder than it is. How many people dislike broccoli and are men? Dislike broccoli, men, 21 dislike broccoli who are men. So it's 21 out of 100. Now, if you wanted to multiply it, you could, right? That's a little bit different. So you could say that that's equal to, let's see, dislike broccoli, 49 out of 100. So it's 49 over 100. Underline that. And you can multiply that by, oops, by, so that would be the first thing. So broccoli, and then is a man. But given that they like that they dislike broccoli. Ooh, sorry. Given that they dislike broccoli. So there's 21 men who dislike broccoli. So given they dislike broccoli, it's 21 over 49. So that'd be 21 over 49. And that's underlined as well. Sorry. And then once you multiply these, right, if you multiply these two things, then you're going to end up getting 21 over 100. So you'll end up with the same answer, because this 49s will cancel right out. So you could do the and as multiply, but you have to remember they're dependent. And like I said, you don't need to do that because it's easy. It's in a table. We've given it to you. Table, you don't do the ands, you just grab them. I'm just proving to you that the and means multiply rule does not go away. It still holds. Okay. So let's take a quick look at this one very quickly. This is from chapter 2. Scores of 20 games for basketball teams given below. Find the range. So range, there's no mid in here. Mid means find the average. No mid, so it's not the average. Instead, it's just going to be find the smallest and the largest and just subtract them, find the difference. So 68 minus 8, that's going to give me 60. Oops, it's going to be slow on me, isn't it? And then, so our range is 60. And then we're going to make a group frequency distribution using 7 classes for the data, including relative and cumulative frequency. All right, so is this 25 or more? Yes. So I'm going to, as long as it's at least 25 or more, then I can totally just do in groups of 5 or 10 or something like that. So do I want 5 or do I want 10s? 7 classes, well, 7 times 5 is only 35, so it's not going to be enough. I'm going to have to go with groups of 10. It seems like that fits it a lot better. 7 times 10, that should be able to accommodate everybody. So I'm going to go by 10s, which means that I take the smallest number, 8, and I find the 10 that's below it. So what's the next 10 down below 8? If I round down to the next 10, it'd be 0, right? So I start with 0, and then I'm going to have class widths of 10, so I'm going to go up by 10s. So it's going to be 0. I'm going to find all of your first ones, your lower limits first. So 0, 10, 20, 30, 40, 50, 60, done. And then what comes before 10? 9. What comes before 20? 19. What comes before 30? 29. And you can see, oh, look, there's a pattern. I can just add 10 here also. Great, so then you get the rest of them. Now, the next question would be, well, what about my frequencies? So then you count up the frequencies. I'm not going to bother to do that because it's just going to take up more time than we want to bother with. So let me just make them up. Right, so these are made up frequencies. These are made up frequencies. And here they are. They're not real, but here they are. And these are just the numbers, right? Frequencies are the actual numbers of how many are in each group. The whole numbers. The relative frequencies are the ratios of these frequencies to the whole, how they relate to the whole. So the first one would be 2 out of 25. So 2 over 25, which as a decimal is 0.08. Next one would be 5 out of 25. So that's 5 out of 25 is 0.20. 6 out of 25, 0.24, 0.16, and so forth. So these relative frequencies are going to be your percentages. And then cumulative is when you accumulate things. When you accumulate things, you just add on to what you have. You keep what you have and you add more, right? When you accumulate all sorts of crap in your house, it just means you add in more add more to what you have already. So here, I have 2. I'm going to start with that. That's the first thing. And then here, I'm going to add 5 more. 7. Here I'm going to add 6 more. 6 plus 7 is 13. So altogether now I have 13 and so forth. So those are that ones. Just to remind you, it's been a while since we've seen those, so I wanted to kind of bring those up again. This is the next problem I want you guys to work on in a group. is this one right here. So go ahead and get in your groups again, and I'll open up the breakout rooms and give you guys 6 minutes to work on this. I think 1, 2, 3, 4. Yeah, sure, 6, 5 or 6. Okay, welcome back everybody. So let's take a look at this one. So first of all, we have 2 red, 4 blue, 5 green, which means we have 11 altogether. So, and my options are, from here we have red, blue, or green. Remember, these are kind of my end destinations. I can go to red, or I can go to blue, or I can go to green. So those should be at the end of your branches. Yours should look exactly like mine. And then the probability should be on the branch itself. What's the probability I go to red? I have 2 reds out of 11. Probably I go to blue, I have 4 out of 11. Green, 5 out of 11. Then, if I picked a red marble, then I'm right here. If I picked a red marble, now I only have 10 marbles left. And only one of them is red because I already took a red one. So I have 1 out of 10 red, but I still have 4 that are blue, so 4 out of 10 chance of blue. And I still have 5 that are green, so 5 out of 10 chance I go to green. If I picked a blue first, then I'm here, which means that I still have 2 red, but now I only have 3 blue because I took one, and I have 5 green. So 2 out of 10 red, 3 out of 10 blue, 5 out of 10 green. And then down here, if I took a green one, now I only have 4 green ones left. I still have 2 red ones, so 2 out of 10 red. I still have 4 blue ones, so 4 out of 10 blue. But now I only have 4 green, so 4 out of 10 green. This is going to be worth a reasonable amount of points because I don't have a whole lot of time to test you on a lot of different things. So, I've got to kind of balance that a bit, and this is going to be a fair amount of your probability points, is making this tree and answering some questions about it. The probability of the first green is either green or red. So green or red. Ors you what, guys? Ors you add. Ors you add. So here, 2 11ths, 5 11ths. 2 plus 5 is 7, so 7 11ths. Blue then red means that I draw a blue one and then I draw a red one. That's an and, really. So blue, then red, that's this purple path here. So remember, as you go along the path, you multiply the probability. So 4 11ths times 2 tenths. 4 11ths times 2 tenths. If you do this part right, and then you screw this up because you forget that when you multiply fractions, you multiply the numerators and you multiply the denominators. So it should really be 8 out of 10, over 110. And then you'll still get most of the points as long as you give me this part first. If you want, go ahead and to multiply them. If you don't know how to multiply fractions, just go ahead and find them as decimals in your calculator and multiply those. It's fine. I'm okay with that. You can give me a decimal answer at the end. That's okay. Okay. Questions about this one before we move on? All right. So then next, this is another problem you're likely to get, something similar. I'm going to go over this one more in depth on Tuesday, but I just want to touch on it a little bit here so you guys are kind of on board with this one. Let's get a reader. Haley, go ahead and read.
Weights of breath that have means of 115 grams and a standard deviation of 16 grams. What is the probability a rat weighs less than 112 grams?
Great.
If you were to random.
Okay, that's good. We'll stop here. So this is a rat. One rat weighs, what's probably a rat weighs less than 112 grams. So this is one rat. So this is your regular normal distribution, normal CDF. So you'd have your steps. Let me show you. So right, you find your z-score, then you draw a picture and shade, and then you use normal CDF to find the area. You guys just did this a little bit ago on exam 2. But here, down here, we're talking about randomly selecting 36 rats. What's probably their mean weight is less than 112. So now we're not talking about one rat, we're talking about 36 rats and their mean. So now we have an n. When you have an n, then you've got to use sigma x bar, right? Sigma over square root of n. And then so then it'll be the same steps, only to find the z-score, you're going to use this sigma instead of just the regular ordinary 16. Right, so you're going to change, that sigma will change, and then other than that, the rest of the steps will be the same. I wanted to spend just a few minutes, we have a few minutes left, I wanted to give you guys a few practice on identifying problems. So take a look at this one and see, let's get a reader. Ashley, go ahead and read.
The researchers surveyed layers in each of 4 regions in the country and asked them if they performed pro bono work. The results are shown here. At alpha point 10, is there enough evidence to reject the claim that the proportion of those who accept pro bono work are the same in each era? Show off steps.
Great. What kind of problem is this? I want to take 15 seconds. Take 10 seconds. Okay, what do you guys think? What do you guys think? I've heard from 3 people. 4 people. 4 people are going to get A's. Okay, so we have categories here. We have labels on top. We have labels on the side. Are these observed and expected? Are yes and no observed and expected, or are they 2 different things? They're 2 different things. Saying yes and saying no are not the same thing. So this is a matrix, chi-squared matrix. Right? You have labels on top and along the side. Oh, and then also, do you see proportions? There are also proportions. That's another dead giveaway. That's got to be a chi-squared. Okay, sorry. 10 seconds for this one. Okay, tell me what you think. 2 people. 3 people. 4, 3 people. Same 3. Right, linear regression. Why? Because I don't have labels up here. And these aren't labels. These are sometimes the same number. These are not labels. These are 2 different things. Right? We have number of absences and final grades, and it's an X and a Y. Right? So I don't have any labels up here. I'd have to have labels up here for this to become a chi-squared. So no labels, can't be a chi-squared. So then is it 2 lists or 3 lists? 3 or more lists, it's only 2 lists. So look for that X, Y, and they're in pairs. So this is linear correlation or regression. And this is chapter 10. Good. And then this is the other thing I might ask you. Then using the results from part C, predict the number of absences for a student who had a final grade of 96. So in other words, final grade of 96. So final grade of 96 is final grade my X or my Y. That's my Y. So then you have to figure out what the X is based upon, well, if you rejected H naught, then you would use that Y equals AX plus B. So if applicable, find the regression line. Only if you rejected H naught. And then I might give you something else saying, well, instead of using alpha as 0.05, use alpha 0.01 and do another hypothesis test and see if you're going to reject H naught or not. And then using these results, predict the number of absences, the number of absences for a student who had a final grade of 96. So maybe it'll be the same, right? Final grade of 96 because maybe you'll use the linear regression line in both cases and they wouldn't change. Or maybe they'll be the same because you used y bar in both cases or x bar in both cases. Or maybe they'll be totally different. But we're saying run the test at alpha is 0.05 and then run the test again at 0.01 and then figure out this is your alpha is 0.05. And this one if alpha is 0.01 and see if you reject H naught and if that makes any difference. Here is the last one, or I think it's the last one. I just want to give you guys a little sense. So what's this one, guys? Yep, I have labels here. Do I have labels there? I do not have labels there. So it is not chi-squared. And instead, I have difference in the averages, the means, right? This is ANOVA. I think that is all I've got. Oh, no, I've got one more. One more. Last one. Good. Yep, I have labels here. I kind of have labels here, except for they're not really. It's really observed and expected. So these aren't really labels. These are really the same thing, only observed and expected. So this is my chi-squared list. 11.1. Okay, great. Thanks again for all of your hard work. You guys are awesome. I'm really going to miss you. I'm so sad we didn't get a chance to meet more in person. Good luck on the final. I hope to see you guys, some of you guys on Tuesday at the review session. Definitely if you're around campus next semester, well, next semester won't be on campus either probably. All right, at any rate, yeah, good luck on the final, and it was really great meeting all of you guys and working with you all. Take care. Have a good night. Have a good weekend. Study hard.